Good morning, Dr. Hazem. Good morning, everybody. I'm just giving the attendees a few minutes before we start the presentation. You're muted.
I was muted. Yes, good morning, Dr. Ahmed, everybody. Thanks for attending.
Thank you. Thanks so much for being with us today. I believe we can start and then anybody can join us. The session is recorded anyway, and we will be sharing the webinar for anybody who's interested to watch it again. First, again, I'd like to welcome everybody, and I'd like especially to welcome Dr. Hazem, who supports us actually all the time whenever we're needing to listen to him and to listen to all the advancement in geotechnical engineering and pile testing in special. So thanks again, Dr. Sarhan. So Dr. Hazem is, as we all know, he's a general manager at AUD Engineering Consultancy. He was a PhD from Houston University and a very wide experience in industry. And he is our expert, as we know, in pile testing specifically. So thanks again, Dr. Hazem, for being with us today. And you can share your screen and start the presentation.
Thank you for this introduction, Dr. Ahmed. My name is Hazem Sarhan. I'm General Manager for AUD Consultants Engineering in UAE. And today's topic is about thermal integrity testing of deep foundations. I don't know if you can see the full.
Yes, we can see the screen. Yeah.
Presentation mode. You see the presentation mode now?
Yes, now we can see it. Yeah.
You see the presentation mode. Okay. So just to start off, you know, why do we test in the first place for the deep foundations? We test because we want to manage the risk. We don't necessarily want to end up with situations in which we have installed piles or drill shafts in the ground that are not really performing as per what the contractor, owner, and the engineer intended. So there's several methods available in the market that enable us to ascertain the quality of the installed deep foundations, mainly the widely used low strain integrity testing, the cross-hole sonic logging, and the testing method in which the concentration of the talk today is going to be around the thermal integrity profiling. So in order to have the required carrying capacity of the pile, you need to have good structural integrity, and you need also to have adequate bearing capacity. And since usually drill shafts are non-redundant, sometimes it's non-redundant, sometimes it's critical in the load carrying, so we cannot really afford failures. So from this aspect, if you want to determine the structural integrity, you can do low strain integrity testing, cross-hole logging testing, or calipers, which is a method. Some methods exist that enable you to look at the shaft geometry before you pour the concrete. And one of the newer methods now we're going to talk about is the thermal integrity profiling. For the geotechnical capacity, of course, we regularly undertaking static load testing, or if the loads are quite huge, we do bidirectional load testing using embedded load cells, or even dynamic load testing, which can also be used to determine the capacity of the pile, including the shaft and end bearing resistance. So several studies have been done that shows, I mean, the aim was to determine what is the percentage of anomalies in the shafts, and two separate studies in 2005 and 2012 roughly agree on the percentage of anomalies that exist within the shafts, the installed shafts. Both of them have a different distribution, but both of them say that most of the anomalies occur at the top or the bottom of the shaft. So the low strain integrity testing is a method that is available or described in ASTM D5882, and the prime function of which is to avoid such situations. It's the primary function of pile integrity test or low strain integrity test is to catch major defects or evaluate questionable shafts. It can easily test many piles within a short period of time, so it's easy to undertake. And there is minimal or no advanced preparation required and no advanced selection required. So it's good also to use as forensic purposes. The method is basically you introduce a stress wave that travels along the shaft. This stress wave gets reflected when there's an impedance variation. In this case, it's the toe. And then the stress signal is then picked up by the accelerometer at the top. So if you have signal input by means of a hammer, a handheld hammer, it travels down the pile length and gets reflected off the toe at a time of L/C, considering the C is the stress wave velocity. Then the accelerometer can then see the reflected wave at a time to L/C. And this is what you can see as a plot of a test record that is showing a shaft that is quite ideal. You have a good input signal. There's no measured anomalies or indications of anomalies along the shaft, and then the reflection on the toe. Now, in case you have a defect along the shaft, what happens is that during the travel of the signal downwards, it encounters this change in the pile cross-section or change in impedance. And say if it's at a location X, then the accelerometer is going to pick up the reflection of that, some of the reflection of that input stress wave travels upwards the pile again and picked up by the accelerometer at the time 2x/c. Then it continues down the pile and gets reflected along the toe and then upwards the pile again. And this can show a signal of a pile that can indicate there's a problem around the midsection of the pile. So this is we consider this to be a major defect. If it's picked up by the low strain integrity test or the pulse echo method, it is usually indicates it's a major problem. So preparation of the pile top in this method, usually you don't get such nice situations in which the pile is clean at very comfortable to test. In many situations, you end up with issues like this one, in which the pile needs to be prepared. You need to remove the loose contaminated or fractured concrete on the top. So you need to have a good smooth surface against which you put your input pulse with the hammer, and also a location in which you can put your accelerometer to record the impulse and the reflection from the pile top. So sometimes if you have a very long steel rebars sticking out and there's no structural need later on, maybe you need to trim it to a minimum. And you can grind flat spots to receive the impact of the hammer and the accelerometer. So you always need to, in the real data in the collection in the field, you need to take as much good information as you can, because that's the information you're going to be using later to make the interpretation. So you need to collect multiple blows, averaging reduces random effects, and you use the best possible equipment and low noise and analog to digital resolution and signal processing options. So in the end, the interpretation looks for good data, consistent and reasonable, similarity or differences for different piles, so you can evaluate if there's something different. Usually, if there's rapid changes in features in the data, it usually indicates that there's a structural component that is the source of the impedance change. If it's a slowly changing feature, usually it's soil related. We definitely like to see a tow signal because this indicates that the stress wave was able to penetrate to the toe and get reflected back. So it gives an indication about the shaft integrity, shaft uniformity, and then the interpretation will, if it sees something, it indicates there's a major defect. It's always good to compare the soil profile, the installation records, especially if you have any doubts or if you think there's something wrong in the signal. So this is always a good this is a good practice to always have a look at the soil profile, and if there's anything showing in the installation record that can give rise to some doubts. So in terms of this test locates major defects. It is limited to general interpretations. It doesn't really give you exact details. And sometimes if you want to read too much into the data and do heroic efforts, it can be maybe over-interpretation of what the data can really tell you. General guidelines about the classifications. AA is a good pile. We have a clear tow response, no obvious defects. The shaft is sound. AB, no indication of a defect up to a depth of X, but maybe there's no clear tow response. So we can say no major defects. If there is an early impedance and decrease in the tow response that is apparent at a depth of X, you can say there's a probable flaw at depth X. If there's a clear indication of a serious defect, then there's a probable defect at the depth X. And if there's a record that shows poor quality, complex geometry, you cannot see a tow signal, then sometimes the record can be inconclusive and it's not going to be suitable to use for the interpretation. As far as the limitations go, there can be limitations on the length over diameter ratio. So usually a rule of thumb of 30, but you can, if there's good conditions, you can see more than that, 40 or even 50 L/D. Equipment and the resolution can see, can see farther than that. If there's a highly non-uniform pile, it will be difficult to interpret. If there is mechanical or joints, also can hinder the interpretation. Of course, also if there is small defects, they're going to be hard to find. Also, when you're inputting the signal, if there's a defect at the top of the shaft, and you cannot see visually, but it's at the top, also may be difficult to detect. And once you detect something, it will not be also very, it will not detect or give you the capacity to determine where the defect is located in which quadrant. In conclusion, this method is fast and expensive. The equipment is mobile and requires excuse me, minimum site support. So you can test many piles on the site. There's no advanced planning required. Minimal pile preparations, pile surface preparation. It finds the major defects, cannot locate defects in the cross-section. They can have potential length limitations. If you have a very non-uniform pile, it would be quite difficult to make an interpretation. If you have cracks or joints, it will usually block the waves. The second method, which just to quickly go have a quick overview about it, is this cross-hole sonic logging, which is described in ASTM D6760. Usually, the recommendation is to have one axis tube every 300 millimeters of shaft diameter. So if you have a 1 meter shaft, you typically have 4 axis tubes. You fill the tubes with water and you put the probes down the tubes, and then when you're pulling the tubes, you start recording the data. So the waves are transmitted from the transmitter and received on the other side. If the concrete is satisfactory, then we can see that in the cross sections that you can take along each 2 pairs of axis tubes. So if you have 4 axis tubes, you're going to do 6 cross sections. So the emitted signal from the transmitter travels along the cross section, and then it's received on the receiver, and there's a transit time. And then if you superimpose these signals along the shaft, it gives you what is traditionally known as a waterfall diagram. And it's quite easy to interpret if something is okay or not okay. So if in this instance, you can see something here that, you know, there's a reduction in signal, so immediately it's very easy to interpret. So if you have the shaft, the reinforcement, the CSL logging tubes, and you do your cross sections, and you say that you have an anomaly, this anomaly, say it intersects the pathway of some of the traveling waves, say between profiles 1 and 4, 2 and 4, and 3 and 4. So if it's within the path of the cross section, it will be easily detected by the CSL. Now imagine another scenario in which you have the anomaly lying outside the reinforcement cage. In this case, you do your test, you do the transmission, but the anomaly lies outside the path of any of the cross sections you're going to test. So it's not going to be easily detected, or may not be detected at all by the CSL method. So if you have, how do we identify defects? If you have a good signal, it's a good strength, there's no delay in the transmission. So usually you have this when you superimpose them on top of each other, this is the sign you see. If there's a delay due to a low strength, due to an occlusion, due to necking, then this is going to create a gap in the data. And here you can easily detect there's a delay and there's something wrong. So usually if you then do a coring and you discover there's, you know, like concrete that is not uniform, you have gaps, you have inclusions, you can then confirm that this really is a defect. And then you can determine what else you can do to rectify. So about the CSL rating, you can have a good signal if the first arrival time is between 0 and 10%, and the energy reduction is less than 6 decibels. Starting to be questionable if it's the fat between 10 and 11 and 20, and the energy reduction is less than 9. Poor, or there's a flaw. So the fat increases up to 30, and the energy reduction from 9 to 12. Then there's a poor, there's a defect if the fat increases more than 31, or you have an energy reduction of more than 12 decibels. So this is a guide by DFI that helps the engineer to make interpretations of the data. So if you have the relative energy reduction plotting versus first arrival time, if you're within this zone, zone A, it's green. So you can say that this is an acceptable result. Everything's okay. If you fall within the yellow zone, you can either conditionally accept it with maybe further assessment. And if you fall in the red zone, then it's a highly abnormal test result, and definitely you need to do something about it, either coring or something else. So if it is category A, you say the data is within normal ranges, no additional assessment is necessary. If it's within category B, you can conditionally accept it. You can filter out the issues if there's if you want to rule out debonding, for example, you can flood the pile top. If you're using a retarder in the concrete and you suspect the concrete is a bit lit green, you wait a longer time. If you want to consider more advanced analysis like tomography to delineate the affected areas, you can definitely do that. So you can consider the number of affected profiles, the depth, the vertical extent, and then you assess the severity. If it's possible, you can excavate for visual assessment if it's near the ground surface, or you can do complementary tests. If it's highly abnormal test result in category C, so it is recommended to drill a core to further identify the extent and the nature of the anomaly, to do a compressive strength test of the concrete core samples. If required to remediate, you can pressure grout or replace the whole plant. So cases show like when to perform a CSL test. This shows the test done in day 1, 2, 3, and 4, and as you wait longer, you definitely have a stronger concrete and better signal. So at day 4, and what in day 2 may appear to be a questionable result, just by waiting some time, you test again and everything is okay. So the ASTM recommends to test after 3 days. Other specifications require even longer times, like the French, they recommend 7 days. Now, if you have a test results like that indicating a top anomaly, you do a core, and during the records, it showed that it was placed through a water, and because there was a tremor problem, so definitely there was a contamination. So this was picked up readily by the CSL and confirmed by the core. This shows a problem towards the toe of the pile. There's a minimal or no recovery after doing the core. This is a test just to see whether the CSL is going to see if there's an anomaly outside the rebar cage. Remember the slide in which we showed the anomaly outside. So in this test, the anomaly was completely outside the rebar cage, and the test was done, and there was nothing was detected because it was outside the intersection of the transmission and the receiver. So if you have debonding, it can show up something like this. If you flood it, the pile top, and you retest after flooding, you can eliminate that false indication that there's a problem. Sometimes there's design issues, and if you have a very heavily reinforced shaft, that this is a recipe for creating voids or anomalies within the concrete if that's not taken into account in the concrete design, for example. And if there is a defect and you want to further interpret the data, like if you have an anomaly within category B, you want to see exactly where that anomaly lies, the quadrant, location, extent. There is an advanced analysis methods using tomography that can assist the engineer to make that interpretation, and based on which they can make then a determination in relation with the engineer. You can tell him this is the interpretation of the result, and then there can be further discussion what can be done. You can accept this pile, you can consider it as a reduced capacity. I mean, there is several, as long as it's not a fatal thing that you need to do a drastic intervention, you can use that data further from the tomography to make informed decisions or guide you towards finding a solution with the engineer. The advantage, of course, that's not, compared to the sonic logging, so the pulse echo method, you have no sensitivity to the surrounding soil or pile length. So theoretically, you can test as long as you can put the probe down and pull it up again. So it checks inside the concrete cage by depth and quadrant, so you can know the exact location. Easy for interpretation. Once you have collected good data, it's easy to interpret. The installed tubes, usually when the contractor you see that these tubes are installed, it inspires better construction. And the advanced analysis using tomography is available to assist in the interpretation. Limitations, of course, you have to wait some time to do the test. Axis tubes are required. It cannot see outside the rebar cage. If you have small defects near the tube, can appear to be large. It's susceptible to debonding bleeding, can give false positives and maybe delays and unnecessary pouring. Now this segues us to the method that we want to talk about now, which is the thermal integrity profiling. This is described in the ASTM 7949. And the testing measures, this method measures the elevated temperature during the hydration process during the casting. So the temperature during curing is directly related to the concrete quality, volume, and radius. And the variance in temperature between diametrically opposite wires, because in the end, instead of axis tubes, you put thermal wires with thermal sensors that you thread along the reinforcement, longitudinal reinforcement. And the measured temperature between opposite wires can indicate or give you an indication about cage misalignment or concrete cover issues, which this is the only method that allows you or gives you this flexibility or additional information that you can use. It is always recommended to measure the concrete volume that's installed in the shaft with this method, as then allows you to convert the temperature to radius. So as a summary, the thermal integrity evaluates inside and outside the rebar cage. As opposed to the CSL, it can only see inside. This method can give you 100% coverage of the whole deep foundation. It can allow you to assess the concrete cover as well as the cage misalignment. Again, this is the only method in the market that can give you this flexibility or additional information. Assessment of the integrity can be done during the curing process, so which happens relatively fast, and within 12 hours from placement, you can already see the results of the integrity. So if you are able to see the results of the integrity within a relatively short period of time, this gives advantages in terms of allowing the contractor to get approval and allowing the construction to progress faster if the client requires approvals or regular approvals to continue, or in the end of the project or the foundation installation, it allows you to finish and get approval on the installed shafts faster compared to other methods. So if, for example, you can shave several weeks from the program, construction time is very valuable. And this is something that the contractor and even the owner can appreciate if it enhances or gives an advantage to the project schedule. And again, like described, it's covered in ASTM 7949. Similar to the cross-hole sonic, it's recommended to install the thermal wires along 300 millimeter, every 300 millimeter of the shaft diameter. And it's connected to the longitudinal reinforcement via zip wires. The applications really can cover all the ranges of deep foundations, drilled shafts, auger casts or CFA piles, even micro piles, secant pile walls, and lately for diaphragm walls. So the units is this figure shows a drilled shaft installed, and in which the thermal wires are connected to the data loggers. These data loggers then collect the thermal data points to automatically collected every say 10 or 15 minutes intervals. It is stored within the data logger. This data logger communicates with this unit, which has cellular capabilities in which it can transmit the data to the cloud. And through your setup with the units, you can set up the project and the specific shaft test information. Once you do that, and once these start collecting data on site, you can automatically download the data while you're sitting in your office. So you don't, once you set up the test and it starts collecting data, you don't need to go again to the site to collect the data. So the data is collected automatically, transmitted to the cloud, downloaded by the engineer in the office. So you can set up the the infrastructure in relation to monitoring the data collection. It allows you for early detection of issues. You download the data for analysis, and you can set up your engineer or company account on the cloud, in which allow you to access the data. Now, just to explain a little bit about the theory behind the method, when you install a deep foundation, and during the curing process, you pour the concrete. The concrete during curing, the temperature rises during the curing process, and this temperature dissipates to the surrounding medium. It's the surrounding soil or the air. So if you take a uniform shaft and you average the temperature along the profile, it should give you a constant temperature along the shaft, except the top and the bottom, because you have here more energy dissipation around the top and the bottom. And if a theoretical situation, if you have a perfect cylinder and you have a heat signature being generated due to the curing process, this heat signature looks like a 3D cone structure or surface. Now, if you look at the intersection of the steel cage around this heat dissipation, and if you look at these 2 points, they're equidistant, and assuming that this cage is placed is aligned perfectly within the shaft. So these 2 points intersecting the heat generated from the curing is going to measure the same heat because they're the same distance from the core of the shaft. The core of the shaft, of course, has the highest temperature, and this temperature reduces as you move away from the center. So at these 2 points, if they are placed in the location, the shaft is uniform, doesn't have any anomalies. So you expect that the recorded temperature along the depth of the shaft to coincide with each other. So you expect to have a vertical line of thermal measurements. Now, assuming that you have, like a practical situation, the centralizers of the reinforcement are not placed, or they're misplaced during the installation, and the shaft is misaligned. So you have a cage that may be sitting against the hole. So in this situation, you can see that this point is going to feel more heat along the reinforcement compared to that blue point. This blue point being away from the center of the shaft, closer to the soil interface, is going to be less exposed to less heat compared to that point. So if you then plot these heat signatures and you look at them, and if you see there's a difference between these recorded lines, this immediately gives you the signature that there's a cage misalignment, because if they're aligned, they should read the same temperature. If they're misaligned, one thermal wire is going to be hotter than the other one, and this will show immediately on the graph once you start the interpretation process. Now, assuming that you have an anomaly, and that anomaly is closer to wire W2 than wire W1. So wire W2 at that location is going to feel less heat compared to W1. And that signature is going to look something like this. And here, for example, there's maybe a cage misalignment. So when the wires signatures deviate, that's a misalignment. If you have a reduction in the temperature, this is a signature of an anomaly or a cavity or something that is not as hot as it should be. Conversely, if you have something that, if you have a bulge, or if you have a larger concrete volume, it will emit more heat, and that signature is going to be reversed, it's going to be on the other side. So this immediately allows you to see that there's a defect, and this allows you to shows you that there's a cage shifting. So just an example from the installation process. This is a shaft heat signature during the first hour, after 4.5 hours, 8 hours, and 18 hours. So here it shows that there's a bit of a more heat signature than the rest. So it indicates a larger shaft. So maybe there's a larger volume or a larger concrete volume at the top. Towards the bottom, there is a little bit of cage misalignment. In this case, it was a shaft that is embedded in a rock socket. So during the installation of the rock socket, there might have been some cage misalignment. But generally speaking, looking at this shaft, yes, we expect to have a bulge because at the top there's maybe a bigger cross section. Here, there's nothing showing major defect. There's a bit of cage misalignment. So quickly you can tell the contractor that this shaft is reasonably okay and you can move on. Compare this to another signature that after 2 hours you started seeing something around this depth. As time goes by, the pronouncement of the anomaly is more, and towards when there's a stabilization in the readings, definitely there's something wrong in this shaft. So very quickly you come to detect the problem. The other advantage of detecting the problem early is to the construction sequence may have something. So you can alert the contractor to revise his construction sequence. Maybe there's something inherently wrong that is not suitable to the specific site conditions. So he can take action immediately and avoid having to construct and having lots of problems along the whole site instead of 1 or 2 shafts. So just comparing the two prior to completion and at peak temperature. The peak temperature is at the location where you want to make your interpretation, because this is at the location where the signatures of anything that is abnormal is pronounced. So you can make that interpretation with more confidence. So you, like I said, and it is a good practice to have an accurate volume information, which then is going to allow you to determine the estimate of the radius, and allows you to have a more accurate interpretation of the results. Now, in terms of the criteria, if this has been a recommendation to the DFI, I believe, is that satisfactory S, you have less than 6% radius reduction and the cover criteria is met. So if you have both these criteria satisfied, then you can say that the signature of the shaft in that situation is satisfactory. On the other hand, if the anomaly requiring further investigation, if you have a radius reduction of more than 6%, or the cover criteria is not met. Different foundations depends on the adopted project specification or the country codes or the requirements from the employer. So you can have covers, say 75 millimeter as per ACR, or if ASHTO recommends to have 100 millimeter of cover. So just a quick case histories giving you some flavor about the method, what it can do, and how it can affect the outcome of the testing in general and the project. In this example, this is being presented because it represents time savings. In this particular project, there was 350 drill shafts or board piles, and ranging from 12 to 17 meters, and diameters 1.2 to 2.4. There was a temporary casing installed at the top 8 meters. There was groundwater table at 1.2 meters, and the contractor decided he's going to test all shafts using thermal because of the fast-track nature of the project. Unfortunately, started seeing problems in shaft number 1 around 4 feet, 1.2 meters. There's something definitely not correct. This line shows the cage reinforcement line. So if you have an anomaly that is exposing it's not only not complying with the cover, but also exposing the steel cage is definitely not acceptable. Shaft number 2 showed similar anomalies, shaft number 3, as well as shaft number, and so after 5 or 6 shafts, they hit the pause button and decided to do further investigation, and they did some core samples, and the core samples indicated that there's a problem in that location where the thermal indicated there's a problem. Now, due to the speed of the construction, this is the number of shafts, 6 shafts in which the thermal was able to detect that there's a problem in the construction. Now compare this with this number, which is going to be the number of the piles installed had you been going to be testing using a different method. So maybe close to a third of the piles would have been already installed, and there's something inherently wrong in the installation process, and is going to you will not be able to catch it until you've installed that much, and this much until you receive the report from the testing agency. So it's quite approaching half the shafts on site have been installed, because it's a fast nature, compared to only this number in which you can catch there's a problem using the thermal process. So the summary that 100% of the shafts were tested using thermal. TIP identified there's a problem at the top 1.5 meters after installation of only 6 shafts. There was a groundwater table at 1.2, which was causing washing out of the concrete when the casing was pulled out. The concrete cores confirmed the problem, and the construction techniques were modified to avoid further issues. So in summary, the early detection saved considerable cost and time and delays for the project. Another example, this is a highway in United States, Tacoma, Washington. It's the bridge employed very large diameter shafts and very long, so 3-meter diameter, 38 meters length. So each one of these shafts were instrumented with 10 thermal wires around the circumference. The State Department of Transportation wanted to record the thermal data not only after during the concrete after pouring, but also during the pouring process. So they wanted to use this to say also calibrate or estimate what's the concrete volume that is being poured, being a very big shaft. And so the time interpretation in which at the time during which they took the samples in the beginning was shorter. After then it was maybe 1 minute during the pouring process, and then during the curing it was modified to 10 or 15 minutes. So one shaft showed an anomaly around 90 feet, which about 30 meters, and it shows that this anomaly extends towards the cage, and it shows that there's a significant temperature drop around wires 7, 8, and 9, and this is the 3D plot you get from the interpretation. It gives you a fairly accurate interpretation of where the location of the anomaly and the extent that is around the cross section, and can tell you whether it's only limited to the cover or it extends within the concrete, within the reinforcement cage. In this case, it extended in the concrete reinforcement cage, and this was not acceptable to the client, and they decided to do more coring. And of course, because they think this was the contractor's problem, so they forced them to do many cores, so to make sure that this problem is not extensive. So the concrete scoring results confirm that there's a problem around this length, around this depth, and this was so the interpretation of the thermal was confirmed by the core, concrete core, and it was hydroblasted and pressure grouted to rectify the problem. This is another project in Miami. There's a series of highways and bridges, and all the piles were also the instrumentation of the whole project was done using thermal. And this is just giving an idea about the cost comparison between the two methods, the thermal and the cross-hole logging. So the CSL costs were identified or depending on how many tubes and how many for different shafts, the units, the cost unit of the tubes, the cost unit of the shafts, caps, the cost of the labor, the cost of the post grouting, and so the material cost was estimated about 31,000. This is an estimate in the United States. Of course, each country is going to have different material costs, but it just gives you an indication about an order of magnitude if you compare the methods. If you compare this to the thermal, you calculate how many wires are needed in the different types of shafts, the connections, the labor cost, and the total material cost, which roughly is less than around a little bit more than half the CSL. Now, there's also engineering cost. Now, if you want to do a CSL test, you have to deploy your engineer to the site, or your inspector, or your field expert, and he has to go and collect the data. So 7 site visits, individual tests, analysis, and reporting. This is in comparison to the thermal, in which you only have to do 1 site visit. So there's a third reduction in the engineering time cost. So if you add all these, the material and the engineering costs, you can have a comparison between the CSL and the thermal, which is about half. Now, the time costs, which is not even mentioned here, which can be even more dominant and more with schedule constraints, if you can reduce the time from casting to reporting from 7 days to 20 hours, this is a huge savings. So if you can accumulate all these savings in the project schedule for the contractor, being able to wrap his deployment on site, he can demobilize and save 1 or 2 weeks. This is a huge cost for him, and also for the client. If he's able to shave some weeks from the overall duration of the project, of course, this is welcome to him. He can then utilize the project. So the advantages of this method, it's the ability to analyze, just a quick recap, it's ability to analyze the full cross-section of the shaft, not just inside the reinforcement cage. It is the only method that allows you to analyze cage misalignment, and you can definitely know whether your minimum cover is satisfied or not. It is not sensitive to water debonding or water bleeding. It's always, when it says there's a problem, it is always confirmed that there's a problem. So there's no false positives. So there hasn't been one single case in which the thermal indicated an anomaly or a defect, and it was not confirmed. You don't need to have access tubes. There's no post grouting eliminated. You can have a full temperature record over time. You can accelerate the construction. So you can have the results within 12 to 48 hours compared to the cross-roll from 4 to 7 days. And you, of course, the bigger advantage now is the virtual data collection. So travel restrictions, safety requirements, all these things, are advantages that you don't need to go and visit the site to collect the data. And again, it's not also a function of the skill of the data collector. So the CSL, you have to have a specific technique. You have to pull it in a specific way. You cannot have the transmitters in different locations. So there is techniques, but and once you correctly install the thermal wires, it is the process then automatic. It automatically collects the data, stores it in the data logger, transmit it to the cloud, and you download it in your office. Of course, there's some limitations. You have to pre-plan. Similar to the CSL, you have to pre-plan. In this situation, also you need to pre-plan how many piles I need to test. What is the length of the wires I need to prepare? I need to, the test can only be done during curing. So if you miss that, or if something wrong happens, or if the data, anything during curing process, that's your window through which you collect the data. If you miss that window, then the test is not useful. And then to make more accurate interpretation, you need to have the concrete volumes either through the concrete logs or by any other methods. I think I have managed to complete the presentation within the time, and I want to thank everybody that's attending, and I'm happy to answer any questions if anyone.
Again, thanks so much, Dr. Hazem, for this wonderful presentation. Very informative. And yes, on time this time. We have a few minutes for questions, maybe a question or two. So first of all, there is a question in the chat. I believe you answered it already, but let me just read it. So since the thermal sensors are sacrificial, the cost of testing must be high compared to PIT and CSL. What is the approximate cost per test?
Yeah, I kind of, maybe this was asked before these slides. So I kind of gave a comparison between the relative costs for the tests. The thermal wires, yes, they have a cost, of course, but when you compare it to the CSL tubes, the post-grouting, the deployment of the engineers, and all these things add up. So in the end, if it's not cheaper, it will be comparative. So plus you take all the advantages. You take all the advantages in terms of seeing 100% of the cross section. You resolve any misalignment. You resolve the concrete cover issues, which I think sometimes becomes a heated discussion between the contractor and the engineer. And the engineer is saying, I see the cage on top is like that. How am I to know that it's not the same all over? This method can resolve that, and kill that discussion. So there is a cost for the thermal for sure, but it is a comparable cost to the other CSL method, which is widely used in the.
Is this cost comparison, is it still valid regardless of the size of the project?
Of course, the more volume you have, you can reduce the unit rates. Of course, it depends. So if it's by volume, but this is going to be a case by case. If you have a huge project in which you have many lengths of wires deployed, I believe there can be cost reductions, also further cost reductions.
But even if it was a small project, that's my question. So if it's a small project.
Small project. Okay. Well, small project, again, it's this comparison was based in the United States. Maybe the labor cost there is higher compared to maybe the region, Middle East. Maybe there's different factors. There is also, this comparison was done prior to the pandemic. So I believe material costs now are appreciated even much more, like steel material. So I think this comparison still stands. So you can say that if it's not going to be cheaper, it will not be more expensive compared to the other methods.
Right. Okay, do we have any other questions? So I think the presentation was quite clear by itself. So again, thanks so much, Dr. Sarhan, for this wonderful presentation and for being with us all the time whenever we need you. So thanks so much, and thanks so much for everybody who attended today. And looking forward to see you again in our next webinars. Thank you.
Thanks a lot, everybody, and have a good day forward. Thanks.